Let's get started. Today we will discuss something very important and rather profound idea in the 20th century physics. More often than not, we will encounter systems with interacting particles. As simple as a helium atom, we have two interacting electrons. So in nature, it's very difficult to find a system that is not interacting. So the whole 20th century physics has a large part to do with how to handle particle-particle interactions, in particular, electron-electron interactions. So that happens in atoms, that happens in molecules, that has a lot to do with solids. So in a small piece of metal, you have 10 to the 23 electrons inside, and each pair interact with each other, not to mention each electron also sees all the nuclei in the solid. So you can imagine how complicated such a system is, and yet you know that there is a subject called solid-state physics in which we can do a lot to understand the physics of solids by approximating this very complicated system by an effective single electron Schrödinger equation problem. In particle physics, we also have many charged particles interacting with each other. So hardly you can find any subject that you can avoid considering particle-particle interaction. And I think that may be the first encounter of such a problem in your study of physics in the multi-electron atoms. So today we will discuss the key ideas of how physicists can make progress in such a complicated situation and then reduce it to something that we can handle, and at the end we can understand the whole periodic table. So this is an appreciation of physics, I would say, in addition to the technical aspects. So let me recap what we did last time. Last time, we introduced that any multi-electron atom problem cannot be solved. The key reason is that we have this electron-electron interaction term. It is this term that makes the problem unsolvable, in the sense that we cannot apply separation of variables. If the electron-electron interaction term is not there, then any multi-electron problem is just a pseudo many-body problem, because we can separate electron by electron into single electron Schrödinger equation. It is the Coulomb interaction problem that kills the problem and make it very difficult to do. But that makes physics a lot more interesting. Therefore, either we give up, of course we don't, and then, or we try to simplify or approximate this many electron problem by some effective but approximate single electron problem. So today we will start this discussion of how we can make such approximation and how far we can go. And at the end, how complicated even the single electron problem becomes. So let me start with a big picture of the helium problem. The helium has a nucleus. We assume it to be fixed, so that is no problem. Then we have two electrons. That is the real problem. Last time we already understand that this electron-electron repulsion problem make the problem unsolvable. So today we will see how possible that we can look at one electron between the two electrons. We focus on one electron and try to see the other electron as providing something like an effective potential energy function acting on the electron that I'm looking at. Thereby, this electron will feel two things. It sees the nucleus potential energy function that we know how to write down immediately, and also it feels an average potential energy function due to the second electron. If we can do that, at least at the end, we have an effective single electron Schrödinger equation. So that is the big picture. Okay, so the discussion will lead us through at the end how we can possibly think in terms of this way. Okay, so that is the story. You will see that it is rather difficult, and and actually we need to discuss the problem sorry, in a more humble way, such as we just want to discuss at the beginning the helium ground state. We don't even want to touch the helium excited state at this moment. So we will focus on helium ground state. Now, for those of you who think you have some chemistry background, then you will say, oh, easy. Electron, one of them in 1s, another of them also in 1s, so that I have two electrons in 1s. That is helium ground state. Very good, good for you. The question that we want to discuss now is how we could set up an equation to solve for the so-called helium 1s state. By that very statement, we already make an approximation saying that the problem can be reduced into single electron states called 1s. Remember last time? No separation of variable. We should consider two electron wave function as a whole. When we are thinking about 1s state, we already make an approximation of one electron states that can be applied to helium atom. Okay, so that is something conceptually one needs to understand. So let me start with this part 2 of the chapter. Here, we reduce the complexity of the problem to the simplest multi-electron atom, helium. That is the second element, but that is the first two electron problem. So let us work out something with our tools and see what that need us, or what that hints, give some hint to us and lead us to the next idea. So this is the helium problem. The kinetic energy of electron 1, electron 2. Electron 1 sees the nucleus charge. Electron 2 sees the nuclear charge. And this is the term that kills you. That is the electron-electron repulsive Coulomb interaction. So helium, this is the exact Hamiltonian. But by that, I mean, we ignore spin orbit interaction, we ignore relativistic correction, etc. Okay. The reason is that this is the biggest troublesome term, Coulomb energy, maybe EV in order. All the other things is 10 to the -4 EV in that tiny order. Okay. So we treat the most troublesome thing first. If this is not here, then you look at this one, it's easy. This is like a hydrogen atom, but only the charge of the nucleus becomes 2. Okay, so I call this small h1. It's good, it can be done, okay, solvable. Copy hydrogen result. This is H2, also solvable. It is this part that makes the problem insolvable. And suddenly, something rings in our mind. Now, this is solvable. Out of 5 terms, 4 terms are solvable. Okay, that gives 2 solvable problems for electron 1 and electron 2. Thereby, will it be possible that we try something like perturbation? We take this as a perturbation term, then the unperturbed problem becomes 2, these 4 terms, and they are solvable. So we take that, we apply separation of variables. The solution will be the product of this state, hydrogen ground state, and a hydrogen ground state for electron 2. The unperturbed problem will look like something really like that. Okay? Now that is okay. This is exact for these 4 terms. But when we say this may be a solution for the whole helium atom, that must be an approximation, because the last term does not allow us to factorize the 2 electron wave function. Okay, so formally it's not true, but maybe within some approximation, we can still do it. And this is what we are looking for. We want to do it, okay? Even approximately. So that hints at something that we can try, perturbation theory, right? So with this first 4 terms, indeed, it will give us a product of single electron state. And then without the interaction term, we even know that the wave function is a product of single electron state. The energy will become the sum of the respective eigenenergy for H1 and H2. That's nice. And that just reminds you how we copy result. You have done the hydrogen atom, but helium, the charge of the nucleus is now 2. The only difference is this 2 from here to there, okay? Nonetheless, we can take the result and modify that. The only modification is this, we call this Ez, that is the charge of the nucleus. Then the ground state energy, the ground state wave function will pick up a Ez to the 3/2 power, and then there is a Z also in the exponential of the 1s state. It will also change the Bohr radius because the charge of the nucleus is bigger, the attraction is larger, the Bohr radius will shrink. Okay, so the 1s state will be smaller in orbit. Thereby, the energy will be higher, okay, closer. The attraction is bigger, so the energy will be higher. All right, so this is the energy is it is an interesting exercise. It is 4 times 13.6 if it is charge 2. All right, and then this is the modified 1s state, and this is the modified 1s electron. Okay, so this is old stuff, just modified to charge 2 in the nucleus, not charge 1 in the nucleus as in hydrogen atom. So all in all, what I'm saying is that we know the solution to 4 terms out of 5. So now if we ignore entirely ignore the interaction term. Okay, that is to say, as a zero for the approximation, we only look at these 4 terms. We can solve it exactly. The solution is hydrogen-like. We copy the wave function out. We copy the energy out. This is 4 times minus 13.6. This is for 1 electron. Now we have 2 electrons, okay? So with that, the roughest approximation to a helium ground state is the following. The product is the ground state wave function is the product of single electron state. We know what it is, we copy it out, and the energy will be 4 times minus 13.6 plus another 4 times minus 13.6, so 8 times minus 13.6. This is called 4 times the H3. So let me define what is the H3 for you. H3 is nothing but a unit of energy. It is very popular in atomic and molecular physics. What is it? It is 2 times 13.6 eV, okay? So the hydrogen atom, the ground state energy is minus 0.5 H3. That is the definition of H3. Okay, now that makes sense. This is part of something called the atomic units. If you attend exercise class this week, the TA will explain to you what is the atomic units in the sample question 13. If you don't, you will miss it. Sorry. Okay, you have to attend class as students, please. And I have posted an appendix to this part of the notes, again, about the atomic units. It is just measuring things in the results of hydrogen. For example, we measure distance in the Bohr radius. So when people say it is 1.5, it means 1.5 Bohr radius. Makes sense. It is all what happened in atoms, in bonding in molecules, and in nearest neighbor spacing in solids. It is all around the ballpark of a few angstrom. Why bother with a few angstrom? We just say it is 2 times Bohr radius, 3 times Bohr radius. Makes sense. And energy in atomic and molecular and solid state physics also is around the ballpark of electron volt, because it is the binding energy in atom. So the definition of H3 sets it to be twice the binding, the ground state energy of hydrogen. So it is 27.2 eV. Okay, now let's get back to a helium ground state. Now we ignore everything about the electron-electron interaction term. With such a very rough approximation, the ground state of helium will be predicted to be 4 H3, negative 4 H3, or 8 times minus 13.6. That is to say, minus 108 eV. That is the roughest approximation. But helium atom has been studied in great detail. We know the correct answer. The correct answer is around minus 79 eV. So it is not that negative, meaning it is not that stable. The actual helium atom is less stable. In terms of H3, this is the famous number. minus 2.9 Ha3. That is the helium ground state energy. In terms of Ha3, our guess is minus 4 Ha3. Okay, it's off by about 1 Ha3, off by 27 eV. And nonetheless, it is a good sign for the following reason. When we ignore everything, that means we ignore this Coulomb term, our answer is very stable, okay, minus 108 eV. But we know electron, it is repulsive. By that we mean it will make the total energy less negative. This term is positive, you see, plus E squared over R1 minus R2. So therefore, the actual helium ground state is above our estimation, is good, it's okay. Because this term, when we take it into account, will give a positive contribution. That means it will bring minus 108 up, approaching the actual value. So at least the trend is okay, all right? So that is the story up to now. This is what this picture wants to say. Our roughest estimation, ignoring everything, is here. Actual is here. The difference is about 30 eV 1 Ha3 or so, okay? And we expect if we include the electron repulsion, it will give us a positive contribution, thereby will take this minus 108 up. But does it come to here or it come to there? We have to see, okay? By perturbation theory, we can do an estimation, include this Coulomb repulsion and see whether it will bring the energy to this point, okay, up to here, or bring the energy from minus 108 too much, okay? After all, first order perturbation is an approximation. We don't expect it to bring us to the exact value, all right? So that is the next exercise. So the next thing, we observe that maybe now we can try something like perturbation. So this is like a perturbation term. So what can we do with it? That's the next question. Of course, we have several tools in our box. We can try perturbation. We can try variational method. Okay, we will see how it works out. And at the end, as I introduced at the beginning, what we really do is to approximate the effect of the second electron on the first electron in some kind of effective potential. How could we do it? So that is the path that we will go through, okay? We will try perturbation. We will see what variational method leads us to think towards a better way to approximate what the second electron does to the first electron. All in all, at the end, what we aim at is to save the single electron state picture. We don't want to give it up. The 1s, 2s, 2p picture is just so nice. We want to save the picture, even if it is an approximation, okay? So at the end, we will see how we can develop such an approximation. At the end, that approximation will be generally called independent particle approximation. That is to say, we will approximate interacting electrons into independent electron moving in some rather complicated potential energy function profile provided by the nucleus and all the other electrons. So we have something to do now. After the roughest approximation, ignoring everything, we can solve the problem. That's nice. That is to say, we have to take the unperturbed solution and look for the expectation value of the Coulomb energy term, right? So that is the first order perturbation. So we don't aim at very high stuff. We only want ground state now. So very humble. We just want ground state approximation. So we've solved the unperturbed part, hydrogen light. We only look up the ground state wave function. So this is the ground state hydrogen like ion when the nucleus has plus ZE charge. For our case, Z is 2. Okay, so we plug Z equals 2 here, and there we have the ground state wave function for H1 as well as H2. Okay, for H1, this is R1. For H2, this becomes R2. Our unperturbed state is the product of this phi 1s. There are two factors, one for R1, one for R2. Okay, do you follow me? So now we copy results and see what is the integral to do. This is the perturbation term. The unperturbed state is a 2 electron state that I say it is ground state R1, R2, okay? So first order perturbation give us this expression to calculate. But we know everything. The H prime is this E squared over R1 minus R2 term. Put it here, okay? The ground state wave function for the unperturbed function is something that we know. It is a product of two 1s state, one for R1, one for R2. Okay? What is it? It is, now one of this is this thing with Z equals 2 and R equals R1. The other with Z equals 2 but R equals R2, all right? So thereby it is something like that, okay? With Z equals 2. I have a 2 here because there's one here, there's another one here. Product. Therefore, you get a square. That is the 2 in front. I have yet to substitute Z equals 2 into it. Okay? So now I would like you to stare at this expression for 10 seconds and see whether you understand why we have this expression. You understand this is first order perturbation, nothing new. We are using the tool we developed at the beginning of our course. Is that okay? Okay? So don't be scared. It is just very simple cut in first order expression, okay? Now, but you have to appreciate the complexity as well. It is a 2 electron problem. So the wave function has 6 coordinates, right? X, Y, Z for electron 1, X, Y, Z for electron 2. That is represented by R1 vector and R2 vector. Do you follow me? Okay. Now, this is an energy. You have to integrate over both x, y, z for particle 1 and particle 2. Therefore, it is a 6, what do you call that? Multiple integrals. There are 6 integrals here to do. Okay, do you understand? You understand? Okay. Either you think about it in Cartesian coordinate, x1, x2, x3, no, x1, y1, z1, x2, y2, z2, okay? All in one expression. Or you can think about it as r1 theta 1 phi 1 and r2 theta 2 phi 2, okay? In spherical coordinates. Do you get me? All right. Now, let me tell you something rather profound. I'm hoping that the TA can do one of this integral for you to demonstrate to you. This particular integration, 6 integral in one expression, can be done. Okay. And this can be done, and I give you the answer. The answer of this thing is 5/8 z times a combination of familiar constants. These constants make up one hard tree, or it is 2 times 13.6 eV. And it is positive, as we expect. This makes the helium, the unperturbed part, less stable. It raises the energy, okay? Raised by how much? This is set by hydrogen-like atom because we use hydrogen-like wave function, thereby this thing comes out. And it is 5/8 z. Z is 2 in our case, but I keep it general because I have another application of this answer a little bit later. So take home point. These 6 integrals all in one expression can be done. Okay, now not all of such thing can be done, but this particular one can be done, although it is technically challenging. Okay, so for those students who like integrations, do it, try it before the TA show you how next week, perhaps. Okay, it is rather interesting. You have to, one center, you have a R1, R2, okay? It's easier to do it in spherical coordinate. Then you fix one, you fix one of the, you have R1, R2, you fix that, this don't change. You change this one around. So you do this integration around, okay? And then actually, basically, it is R1, R2, you define an axis between R1, R2, you do all the other things, okay? At the end, you let this one vary and you let this one vary, okay? So this is the technique of doing that. But it is very nice. At the end, you see, very simple answer comes out. It is just like this. In terms of hard tree, the atomic units, many people just quote the result as 5/8 Z because energy will then be measured by hard tree. So now let's put the answer together. Without first order perturbation, we know the answer. It is -108 eV or -4 hard tree. We know that, okay? And then with first order perturbation, it is this thing. In SI unit, left-hand side, or in atomic units, right-hand side. Okay, it doesn't matter. It depends on how you measure things, right? So if I measure it, give it in terms of Hartree, I will have -4. That is -108. And then 5/8Z, okay, that is 5/4 Hartree. So you see, the unstable effect due to electron-electron repulsion will provide something like 1.25 Hartree, above -108. It will take it up, okay, maybe too high compared to the exact value. So at the end, if we plug Z is 2 into here, okay, you will see first order perturbations give something already quite meaningful. It is too stable. The electron repulsion make it less stable by this amount. The total becomes -2.75 Hartree. It means in SI unit, -74.83 eV. So let's see how it does. I mark the known value here. Okay, this is -79 or -2.9 Hartree, depending on what unit you like. And that is the roughest approximation, ignoring Coulomb repulsion. Now with Coulomb repulsion, but treating it only within first order perturbation theory, we have brought the energy up to -2.75 Hartree or -75 eV. Okay, so you see, it has brought the energy too high compared to the actual value. Nonetheless, you must appreciate, previously it is far off, but now it is not too bad. Okay, it's very close. It is -75 eV versus -79 eV. It's only off by 4 eV. Okay, but 4 eV is appreciable. It's not small, but it's much better. Even we only do the simplest first order perturbation theory. Okay, we should be happy, I think. Okay, optimistic at least, right? That has bring us right pretty close to the actual value. Okay, instead of 4 eV is very bad, okay? then you will be a very sad person. Okay, so it's not bad, not bad. So now let's do something even more interesting. So that's the end of the first order perturbation exercise. We try this and see what happened. The result is, it makes sense. With first order perturbation, the Coulomb repulsion makes the answer less stable, thereby bring the very stable energy up, but a little bit too high. That's the story up to now, okay? But at least this hints at our approach makes sense. All right, so now let's see what we can do next, okay? The next thing we try is very important in concept. Let's see what we can do now. In the perturbation exercise, this is our zeroth order wave function. And we use the exact form, so we have this as our zeroth order wave function. And in doing perturbation, because the unperturbed part is defined And it is defined by Z equals 2. So we must plug Z equals 2 into here and then do the integration. And we get the result, okay? And now, how about this? We use this form, but we don't use Z equals 2. But use Z as a variational parameter. Okay, now I pause here to see whether you understand the idea first. I have a helium Hamiltonian, so I have a problem. Now, I introduce a trial wave function with a variational parameter. The variational parameter is the Z in the highlighted part on the screen, okay? So do you follow me? Is that okay? Do you understand what is the next thing to do? Okay. The helium Hamiltonian has the 2 in the nuclear charge, no problem, but it also has a Coulomb repulsion term. I take the whole thing as the Hamiltonian. I have a trial wave function. Now I can calculate the expectation value, vary Z, and find the minimum value. Get me? Okay. So that is our second attempt. Second attempt at getting at the helium ground state energy. Okay. Again, no new technique. We are exercising what we know. That's how physicists do physics, right? Your technique is finite. You have a finite box of techniques, and thereby with a problem, try this, try that, and see whether this works better than the other, right? Okay. So if we do that, we will expect this will give us a value by variational principle that must be higher than the actual one, right? So we expect if we do this, it will still be higher than the actual value, okay? And now I will tell you the result, okay? So now the exercise becomes, take this Hamiltonian, make this the trial wave function, work out the expectation value, and then try to vary Z to minimize the expectation value. There will be no new integral you need to do, luckily, because if you carry this exercise out, you will encounter integration of this form again. But only that Z now is not 2. It's just an Z. You want to keep it as Z. Later on, you do variation on Z, okay? So we can kill 2 birds at once. That's the nice thing, all right? So if you do that, at the end, the expectation value comes out to be a function of Z, of course. It is our variational parameter. And then we can vary Z to look at the optimum value of Z and then look for the best guess for the helium ground state energy, okay? Using this, take the derivative, set it to 0. The optimum Z value is rather strange, 27/16, which is 1.6875. Now, first of all, it is not an integer. Z at the very beginning was meant to be the nuclear charge the charge that the electron sees. Pay attention to the very last phrase that I use. It is meant to be the charge that the electron sees from the nucleus. Okay? If we make the approximation that the wave function can be written as a product of single electron states. Now, look at the trial wave function. It is a product of single electron states. So we are making an approximation of the form of the helium ground state wave function, pretending that the electrons are independent. And at the end, the result says, it looks as if the electron is seeing a less than +2 nuclear charge. It is positive 1.6875 charge. Okay. Now, for those who have come to university through, primary school, secondary school, you must have heard something about screening. Have you? In Chinese, this is called a 屏蔽效应, 屏蔽效应. Have you heard about this? Okay. I think now, maybe the first time in your education, you really see this in a quantitative way. So here the story, let me summarize this variational exercise. It is telling us, shielding, right? But screening is more the technical term, okay? So here for the first time, you see this effect quantitatively. When we make the assumption as if the two electron problem can be treated as single electron problem, this form already implicitly assume there is something like a 1s state for one electron multiply into a 1s state of the second electron, okay? Then at the end, the result says the electron sees a fractional positive charge from the nucleus. Of course, that sounds very strange, but basically it is hinting at the nuclear charge is +2e, okay? Is nuclear charge, okay? No doubt about that. Now, if we focus on one electron, the second electron living in such a state, it is spreading itself out according to this wave function. Thereby, if we look at electron 1, R1, and the second electron is spreading itself like that, it is screening out some of the +2 positive charge. Effectively, one electron is seeing a +2e minus a bit charge. Okay, so that minus a bit is the screening due to the other electron. Okay, that is why you have, I think you have encountered arguments of such screening effect in the past. But here it is one way to really see it out from calculation. Okay, so now the big idea from this exercise is that it started to tell us something of the following concept. We have the +e nucleus, no doubt, but the other electrons, it looks as if it is producing an effective potential that will cancel out some of this +2 charge. Our result tells us that the behavior is like there is a effective charge being 1.6 something, being this, sitting in a Coulomb potential that will give us a wave function of the form like this, but with this particular Z equals 1.68 something, all right? So now we have this idea of an effective potential affecting a single electron. So that is the big idea, comes from the variational concept, okay? So there may be an effective potential energy function acting on a single electron, okay, that will provide us a effective Schrödinger equation for one electron, okay? And that one electron is living in a helium, so a many electron problem, okay? So that is a big development in concept using a hint coming from variational calculation, okay? It hints at a way to handle what the second electron does to the first electron. It may be doing some screening. And analytically, it may be providing a term combining with the nucleus term, give us an effective single electron potential. If that is the case, we can approximate many electron atom as single electron Schrödinger equation problem, okay? And that is the hint. So let me summarize this two exercise. First order perturbation, already pretty good, bring us quite close. And then with variational calculation, it gives us an important idea. We may be possible to reduce many electron interacting problem to single electron problem. And hopefully we can find some effective potential that include two effects. Effect of the nucleus is there, no doubt. And the effect of the other electrons on one electron that we are focusing, okay? And that is a big idea that has led to many branches of physics. In atoms, in molecules, in solids, and also there is a course called many-body physics in the postgraduate level, for example, in this semester, and that has to do with how to handle this problem. How well we can do this, reducing many electron problem to single electron problem. How can we justify this approximation? And what if we cannot take into account all the effects by this approximation? How to do the remaining effect? And that is the advanced course called many-body physics. Okay, so I will take a break here, and then we will hit at the most important idea. What is the Hartree approximation in helium ground state calculation? Okay, so let's take a break now, and we will assume a few minutes later.